So good morning, everybody, and welcome. I'm glad you're here. We've got the organ been pulled forward. I guess this is for Convocation, just happening pretty soon. So that's actually what happens during reading week. You may wonder why that there's a week of November where we don't meet, and it's actually because of this classroom. This classroom is occupied by a fall convocation during that week, so they closed the entire university, which is funny. Ioana, thank you very much for grabbing the microphone. She's already told me about a question about chapter 6 problems. There was one about Mars. You're standing on a scale on Mars, and the idea is if you're standing on a scale on a planet, like on the equator, for example, that planet is spinning around. So you're actually moving in a circular path, which means that you have to have acceleration downward. So when you think about your force diagram, you've got normal force and mg. If you're not accelerating, normal force equals mg, and that's usually the assumption we make. But I guess if you're going in a circular path, you have a downward, or towards the center, which is down, acceleration of v squared over r. And there's another way of putting it in terms of the period, and you can solve out for the period. If the period is the time that it takes to go all the way around. So it's almost like a circular orbit question, but just in terms of a spinning planet. So hopefully that helps that question. But if you want to type stuff onto the ed discussion, I might read it out for you. I was in the middle, do you remember this? I was right in the middle of this question about the Hummer and the Toyota. We were trying to figure out who was at fault. And I'm still curious, because I don't know, I have this intrinsic kind of distrust of people driving Hummers, but maybe, let's just see, because I drive a Toyota. But let's just see. What were we doing here? So let's review. We said, assume no external impulse during the collision. There they are. Hummer was driving south. We don't know the velocity. The Toyota was driving east. We don't know the velocity. We just know the direction, but we don't know actually the speed. But we know their masses, and we know in the end they're traveling at this final velocity, which is 32 degrees east of south, and it goes a certain distance, 10 meters, before stopping. And hopefully the police know what the coefficient of kinetic friction is between the wheels and the ground, so you can use that 10 meters to solve back using a kinematics equation and get that velocity right after the collision. So sort of broke it down into two segments. We already started with the collision, and we found something like this. The velocity is initial, of the sliding motion, which is final of the collision, square root of 2 mu k g times d, that distance of sliding. So I think what I want to start here is with the collision first, now that we have that. So we first did segment 2, and now we're going to do segment 1, which is the collision. And if you want to write that out in terms of x and y, you've got the p initial plus the j is equal to the p final. So what's happening is in the x direction, the Toyota is moving forward, the Hummer is not moving at all, and then there's no external impulse, and you get all of that final momentum of the blob, I guess, is coming from the Toyota in the x direction. But in the y direction, it's sort of the opposite. The Hummer, The Hummer is going negative, right? Because it's going south. The Toyota is not moving at all. There's the Hummer, plus no external impulse. So you're going to have a negative total of the blob P final. So this is P final x. So in terms of representing that mathematically, the mass of the Toyota times the initial Toyota speed, which is what we're trying to find, plus 0 of the Hummer, plus 0 of the external impulse, equals the mass of the combined mass times V final times sine of theta, because it's going at that angle. Maybe call that equation 1. And then the y is, the Toyota is doesn't move in this north direction, minus mass of the Hummer, the Hummer initial, and then there's no external impulse. Here equals negative the combined mass times V final, and this one's times cosine theta. We'll call that equation 2. So equation 1 gives you the speed of the Toyota is this combined mass, I think, divided by the mass of the Toyota times square root of 2 mu sub k. I'm just plugging in this for V final. V final of the collision, because it's the next segment, times g times d. And don't forget to multiply it times the sine theta. And the second equation from the y gives you the speed of the Hummer. So we're almost done here. Divided by mass of the Hummer. Same thing, 2 mu sub k times g times d. That's how far the combined mass slides, times cosine theta. I've just sort of shifted it over, changed the color a little bit, and I've got, we plug in the numbers now. V Toyota initial equals, it's 1200 plus 3400, right? Divided by 1200 times the square root of 2 times 0.8 was the coefficient of kinetic friction times 9.8 times the 10 meters. Multiply those all together and times sine of 32 degrees. When I put all that in my calculator, I got 28.2. Oh, meters per second, right? And then similarly, I think that the Hummer, plugging in the numbers, I got 13.9. It's much more massive, but it's a slower velocity. So actually, VT initial is, I think if you times it by, you want to convert it to kilometers, right? So I'm going to get rid of meters. So you can divide by 1,000 is 1 kilometer, and you want to multiply, you want to get, instead of seconds, hours, so I want per hour. Cancel out the seconds. I know there's 3,600 seconds in 1 hour. So I'm going to basically multiply by 3.6, and I get 102 kilometers per hour in a 50 zone. Okay. So the Toyota's at fault. There you go. So that's that. How are we doing? Everybody? So again, that's chapter 6. We haven't really gotten into chapter 7 yet, but that's the plan for today. I have one more chapter 6 sort of review question for you. If we're good with this. And it's a learning catalytics question, so I thought I'd put that here. You've got a 1 kilogram block dropped from a height of 1 meter above the floor, and when it collides with the floor, it takes 1 millisecond to come to a complete stop. We've got a lot of ones here, but basic, you can imagine it. Something goes clunk, lands on the ground, and does not bounce, but it does stop, so there's an impulse there. The question is, what is the magnitude of the average force of the floor on the block during the collision? So during that 1 milliseconds, or 10 to the minus 3 seconds. So this takes a little bit of calculation, and I'll do it, but just see if you can kind of guess it or quickly calculate it. Maybe I'll give you 2 minutes to think about this one. It's a test. It's a pop quiz. Probably noticed this is 2 segments of motion. Got 1 more minute. See if you can get an answer. Hopefully you're comparing with your neighbor at this point. Okay, guys. Sorry to put you through this on a Monday morning, but let's just do it. Actually, let's see what you guys got. Should we wait? Still working? A little more time? I do not want to rush you. I can tell you there is a sort of a big spread, but the least popular answers are A and D, I'll tell you that. And sort of a third of you for voting for B, a third of you voting for C, a third of you voting for E. I can just sort of read it off there. But let me start us off. What I think is that there's 2 segments. One is the free fall. That's a review. A distance h at acceleration is equal to 9.8 meters per second squared. And then 2, there's 1, is collision with the floor, the chapter 6 part. So we just split it up into 2 different parts. And what we're going to do is sort of neglect any distance it travels during that collision. But delta t is the 10 to the minus 3 seconds. So I think segment 1, we're going to use, I used equation for my age sheet 2.7, which was 2AH is V final squared minus V initial squared, something like that. And V initial, it's dropped from rest. So V final, I think, is square root 2 times G times H. So that's how I started it. And this gives you the final velocity, V final, I think we'll be able to call it V final 1, is equal to 4.43 meters per second. And then for segment 2, again, once I write down this, I think I'm going to stop the voting. So hopefully you voted in. V final 1 equals V initial of 2. 4.43 meters per second. And V final of 2 is 0. It stops. So if we're going to do momentum bar charts or something like that, it looks something like this. This is P initial, Y is negative, J, Y is positive, equals 0. It stops. Ooh, things have shifted on the voting. Going once, going twice. All right, let's see how we did. Shifted over to E. A little bit more than half of you voted for E, which was the one I liked. Let's see if for some reason D was unpopular, but so yeah. So from this sort of momentum bar chart, what you've got is that P initial in the y direction plus J sub y equals P sub final y, which is 0. So negative mv initial 2 plus Fy delta t equals 0. So this Fy is equal to m times V initial 2 divided by delta t. So it's 1 times the 4.43 divided by 10 to the minus 3. And I got 4,430 newtons. If you do everything in SI units, so if your masses are in kilograms, and if your speed is in meters per second, and the time's in seconds, then it all works out so that the force in the impulse momentum theorem is in newtons. So that's going to be important for your practicals this week, because I think sometimes that motion sensor gives centimeters per second, so you better be sure that you convert it to meters per second if your force sensor reads in newtons. Okay, so I got E. Closest one. Are we good? Good? Okay. And sometimes when I think about gravitational potential energy in this room in particular, I think about that MacBook on that balcony, just sitting right at the edge there. And I always think about all its gravitational potential energy and what would happen if it probably fall right on that guy's head, but okay. Hasn't happened yet, so. All right, so this idea of conservation laws can be thought of very simply, is that if you have 10 oranges in your bag, you give away 2 oranges to your friend, you may want to wonder how many oranges are left in the bag, and without even opening the bag, you can say that there's 8. Because you assume there's 10 oranges in the universe. You define a system to be the bag. If you remove some, then you're going to have less in there. But in the universe that includes your friend and the bag, the number of oranges is a constant. You cannot change. It's conservation of oranges. And this could be violated, I guess, if you have an orange tree in your backyard, which I was living in California. I had an orange tree in my backyard. It was great. So in physics, oranges are actually not conserved. But there are things in physics that are conserved. Momentum and energy. And we think these are universal laws. So we've been teaching you Newtonian mechanics and Newton's laws, all of which are approximations. These two ideas, conservation of momentum and conservation of energy, we believe are exact real laws of the universe that do apply and seem to apply even at very high energies and particle accelerators and quasars at the edge of the universe and that kind of stuff. So some quantities stay the same while others change. For example, and this is again back to the whole conservation of oranges. So something at the beginning equals something at the end. And then if you have a system, which is not the universe, then you can have external changes. An external change in the momentum is coming from force delta t, and that's called the impulse. An external change in the energy is called the work, and that's the force times the distance. So that's our concept, our new concept, which is work. That's what I'm going to talk about today. Called the work-energy theorem. Same as impulse-momentum theorem. Impulse changes momentum. So you got impulse-momentum theorem, which is that the initial momentum plus the impulse equals the final momentum. The work-energy theorem is exactly the same, except with scalars, so it's even easier. You got the initial energy plus the work equals the final energy. So what is energy? Energy is a property of an object, like that laptop. Every object that is moving has some kinetic energy, and any object that exists in a gravitational field has gravitational potential energy. Energy has units. It can be measured. I'll just write down what those are. The SI unit that we're going to use in this class is called the joule. Is J-O. It's named after some kind of physicist. And energy is relative. In the same way that velocity is relative, kinetic energy is also relative. So you might say that a car going along past a tree on the side of the road has a lot of kinetic energy. And that's true from the tree's perspective. But if you look at the car and you consider yourself to be in the car to be like at rest, then it's actually the tree that has a whole lot of kinetic energy as it zooms past you. And both descriptions of the universe are correct. But kinetic energy of motion, there's the equation for it. K equals 1/2 mv squared. The units, this also shows the units here, where the joule comes from, is kilograms, is the m, times meters squared per second squared equals a joule. Okay, so that's one good equation to have in your 8 sheet. Kinetic energy, something moving. Then there's position. This turns out to be mgy. So that's kind of interesting. I think I want to do a units check here, because this is a very different looking equation. Units check. But it's the energy of height. So again, that laptop is up on the balcony. It's way high up. And so that h is very high. And the idea is that if h decreased for some reason, like you were to shove it off the balcony, then the kinetic energy would increase. And there would be a conservation of energy as it fell. So 8 mgy decreases as it falls, and 1/2 mv squared increases at the exact same rate until it smashes to bits on the floor there. Remember, g here is 9.8 meters per seconds squared. So you've got kilograms as mass times meters per second squared times y, which is in meters. So that's good. You get kilograms meters squared per second squared, which is a joule. So this is the same units as the 1/2 mv squared, actually. It just looks a little different. There's other equations. I want to show you the Hooke's law one. If you have a spring and there is a spring constant, K is called the spring constant in newtons per meter. Newtons per meter. Then you can have 1/2 kx squared, where x is the distance that the end of the spring is displaced from equilibrium. The end of the spring is displaced from equilibrium. So a spring in which the end of it is at equilibrium has zero energy, and then if you move it, it picks up energy. There's other forms of energy I think I'll just mention. Thermal energy. Okay, hot lava has a lot of internal energy. It's even kind of glowing from it. And we think this has to do with random motions of the molecules, and that's inside there. Proportional to the temperature in Kelvin, by the way. Okay, and I think those are all the ones I want to go through. But we can do a demo. This is a kind of a fun one. So University of Toronto Physics has its own meme, which I don't know if you've ever seen. It's my friend Stephen. And he did this. So I brought this exact same stack of dominoes. You're going to see it in real life. A domino is a rectangular solid. You can play dominoes with it, but you can also balance a domino on its edge. And when standing upright, its gravitational potential energy is a maximum. So the way you kind of look at it is if you do U sub G versus like the tilt, okay, in like theta, then it kind of looks like this. This is when it's standing right upright. Okay. So if you tilt it to the right or you tilt it to the left, it starts to, same way that laptop, if it fell, it would lose some of its gravitational potential energy, so it would gain kinetic energy. And so it's unstable to tipping. If it starts tipping, it wants to keep on tipping. And as it tips, it gets faster and faster, picks up the gravitational potential energy, and moves it. So this is called unstable equilibrium. A small perturbation can cause the domino to fall, transforming its gravitational potential energy into kinetic energy. And as it's falling, if it's sitting right next to another domino, it can perturb that other domino and release its energy. So this is called a chain reaction. And the thing that Pius has set up over here is this fact that, can you switch it to aux, please? It turns out that a domino can knock over a bigger domino that's at most 1.5 times the size of the original domino. Let's see. Our demo. There it is. Okay. So this is a sequence of dominoes. The first one is down here. It is about a centimeter tall and a millimeter thick. And then each domino is 1.5 times bigger than the previous one. I've removed this one just for safety. Put it in there. My hands are so shaky that it's very, very dangerous to do this. There we go. Okay, so now they're all set up. So that the last domino, 1, 2, 3, 4, this is like 13 dominoes. This one is huge, okay? It's like about 100 pounds. And so the question is, what's going to happen if I knock down the tiniest little one? Just give it a little bit of input energy. My shaky hand. Okay. So that's a chain reaction. You have a huge, you would have died if you'd sit over there, okay? Because it's such a big thing. And so the question is, if I just put in a little bit of energy there, where did all that energy come from? Well, it came from Pius. When he set this whole thing up, he had to do work on these bricks to get them to stand up. And I'm not on there, but we can stand up this one. If I pick it up, I have to push this thing upwards, like this, and then tilt it like that. And when I push it up, I'm adding gravitational potential energy. And all I'm doing when I hit it with the tweezers is I'm releasing that energy and getting it back. Thank you very much. And I think that the other interesting thing, this is 13 dominoes. If you had, I think it's 26 dominoes like that, then the last domino would be the size of the Empire State Building, and it would also fall over like that. So that's a geometric growth there, progression. Okay, so I talked about work. If I push a domino up onto its edge, I'm pushing a distance, and so I'm adding energy to the system. So force and distance. So this guy pushing a wall is not doing any work, kind of interestingly, because the wall is not moving. Two things have to happen. Something has to be pushed with a force, and it has to move some distance. And the equation is W equals F d cos theta, where theta is the angle between the force and the displacement. So two things occur whenever work is done: application of a force and a movement of something by that force. So the unit of work is Newton times meter. Again, let's do a units check, because I'm a little skeptical about those units. How's a Newton times meter? So a Newton is, do you remember what that is? If you do F equals ma, I think a Newton is a kilogram times a meters per second squared. So work, newtons times meters, is going to be kilograms meters per second squared times meter. Oh yeah, so we're good. Again, it's the kilograms meters squared per second squared. So we're back to joules again. So that's okay. I always like to check my units with these ones. As long as we're using SI, then a Newton times a meter gives you a joule again. And there's sort of three situations that keep coming up with a theta. So cos theta, cos of 0 is 1, if you remember that. Cos of 90 degrees is 0. And then cos of 180 degrees is negative 1. Remember what cos looks like? Sometimes I like to draw this little smile, which is cos versus theta. And so it starts at 1. This is 90 degrees. And this is 180. This is the negative 1. So that's going to be important to look at the three different situations, which situation 1 is when the displacement and the force are in the same direction, then you're kind of helping the thing go along, and you've got theta is 0. So remember, work is equal to F d cosine theta. The angle here is theta equals 0, and so cosine theta is equal to 1, and so the work is just equal to F times d. That's kind of the easiest situation. Normally things move in the same direction you push them, right? But sometimes they don't. Sometimes, for example, and I did this, I talked about this at the very end of class on Friday. I talked about a woman carrying a bag sideways. So this can happen. The force of your hand in the briefcase, or this bag here, could be not in the direction that it moves for some reason. And if that happens, then your force is not contributing to the work. So this is the angle. Theta is 90 degrees. And then cosine of 90 is equal to 0. So work equals 0 in this particular case. So you can imagine me just walking along constant velocity, applying an upward force to the briefcase. So it has a displacement, it has a force acting on it, but I'm not doing work on the briefcase. And therefore, I'm not changing its energy. It's an external force which doesn't do energy. You want to know you're okay with it? Okay. And then third thing, this is bizarre. What you have to imagine is that it's got some initial velocity to the right, and I'm trying to slow it down with an external force. Does that make sense? And this happens quite a lot with kinetic friction. If I have this puck sliding towards the right like that, kinetic friction is actually exerting a force opposite the displacement. So in that case, theta is 180 degrees. This is theta. Because the displacement and the applied force on the object are in opposite directions, and it turns out the cosine of 180 on your calculator is -1. So in this case, the work equals negative force times distance. It's called negative work. So positive work means you're adding energy to a system. Negative work means that you're removing energy from the system somehow with the force that you're doing. And that's what we say with friction. It removes energy from the system. You define the system to be that puck, and if it slows down and stops, you've taken away all its kinetic energy somehow. So we say that the friction has done negative work. Okay, let's do a quick learning catalytics. This one's not too bad. First one was terrible, I have to admit. These ones should be much easier. But there's 3 in a row, and it's going to be the bench press. So first thing you're going to do with the bench press is push upwards on the bar with a force of 200 newtons, and the bar goes a distance of 0.3 meters up. So what's the work that Vaibhav does on the bar during that distance? One minute. And then the next 2 questions are going to be about the exact same situation. Okay, 5 seconds. Sorry to rush you. Yep. Yes, question? Yeah, it's a really good question. It's a constant velocity, so net force is 0. So this is not a force diagram. Force diagram would have mg going down as well. But what I'm asking here is the interaction of Vaibhav on the bar. Is there work done on the bar by Vaibhav? So I haven't included the work that the Earth does on the bar. Okay. That's a really good point from the front row here. There's no network that's going to be done on it. Good point. Anyway, going once, going twice. And stop. So 0 was not the answer I was looking for here. I was looking for something positive. So it was either A or B, and people like A. So let's do a check there. So I think, again, theta equals 0, so that's why this is positive. So it's just W equals FD. So it's, you're applying a force, it's very simple. You apply a force of 200 newtons on it, and it moves in that same direction, a distance of 0.3 meters. So I would say there you've done 60 joules of work on the bar. And the next question is you lower it back down. Sorry. Click. Nope. Wrong, I totally screwed that up. Okay. I don't know what that's going to do to my gradebook, but hopefully you now have a question. Same question, but how much work does Weber do? And this is weird. He's lowering it down at a constant velocity while pushing upwards with a force of 200 newtons. Again, it's in equilibrium in both cases, but it's moving. We're going to run out of time here. Should we care to do the spring one next video? Yeah, okay, great. Okay. Going once, going twice. Survey says up top 2. People are saying D, which I like. That's so the theta is 180 in that case. You're pushing in the opposite direction. So I would just sort of draw, this is the force of Weber on the bar is up. Oops, on. And the displacement is down. So theta is 180 degrees. So cosine theta is -1, and you get -60. And then the next question is, what about the entire motion? Just add the two works, I guess. He first pushes up and then pushes down. How much work does it take to do one bench press? Okay. And hint here, I think the reason here is that the displacement is equal to 0. Okay. So hopefully you guys got that. And another way of putting it is that you first do positive work plus 60, then -60, and they add up to be 0 or something. Seems like a lot of work, but in physics, it's just force times displacement. Joanna, yes?
Somebody asks, since a Newton times a meter is a joule, does that mean that torque measured in Newton meters can also be said to be measured in joules? Since torque isn't a type of energy, that seems wrong to me. I know we haven't covered torque yet, but this still confuses me. What's going on with the torque units?
Yeah, it's a good question. It's a couple weeks ahead, because we haven't covered torque yet, but we certainly will, and that is correct that torque is a force times a distance, but it's definitely not a joule. It's kind of an interesting question. So certainly what we're doing with work is the vectors have to kind of be in the same direction or opposite direction to have non-zero work. And torque is completely different. You have a cross product there where they actually have to be at right angles. And if something's not moving, you've got a lever arm. And so when you push a lever arm at a right angle, that's when you get positive torque. So it's a different concept, but I think coincidentally it has the same units. You would never call a torque a joule. Interesting question, though. Oops. Should we go back to the top one? There we go. Okay. Yeah, I think that's all the... We'll see how far we get here, but going a little slow. So basically, I told you before, the impulse momentum theorem, you've got some initial momentum plus the impulse equals the final momentum. This is called the work energy principle. The initial energy plus the work done, so the work is an external force in your system, gives you the final energy. So it's kind of like conservation, but now you've got an external force applied over some distance. So, and the example we're going to do, we might as well do it here, but let's go through the slide first. A spring-loaded toy gun is used to shoot a ball of mass m straight up into the air. The spring has some spring constant k. The ball has some speed vb just as it leaves the barrel, and then it goes up a little to some maximum height. So we define the system to be, in this case, the ball plus the spring plus the earth. So somehow in Chapter 7, this is a bit of a foggy concept, but we include the gravitational force of the earth in the system. So we say that this gravity force is an internal force, not an external force. We don't talk about the very good question, which is what happens during this bench press of the gravity, the work that the gravity does on the bar. We call that an internal force. That's why we use gravitational potential energy. And we say that something that's up has greater potential energy, more energy. So it looks like this. What the heck are all those things? Yeah. So what we did is we took the energy and we split it up into different types of energy. So energy can kind of be kinetic, it could be gravitational, or it could be spring. So you just add them all up. And the same thing for the final. It could be kinetic, or it could be gravitational, or it could be the spring. So you add those all up. And that's how you generally do these conservation problems, is you take all the different forms of energy and you add them all up, and you say that's equal to the final energy. And then work, oh yeah, but except for the work. The work is done on the system by things outside the system. So if we include the spring and the earth in the system, then there is no work done on this. And so you have conservation of energy. So in our case, W equals 0. So maybe we should do it just for fun. And then I'll go through some of the analysis. It's just oxplate. You gotta teach me how to do it. Thank you very much. So here we have ball. Here we have a spring. It's all loaded. Pius has already pushed it in with this. If we pull the thingy, this way I guess, boing, it goes way up. So and we're going to analyze 3 steps. The initial, when it's sitting with a compressed spring, that's got a lot of stored energy, but it actually doesn't have very much gravitational potential energy. Then it goes up to here. That's where the spring has lost all of its potential energy because it's at equilibrium now. The ball is just at the kind of launch point, I guess. Maybe it should be right here, right when it just loses touch with the spring, actually, not the container. It's when it stops touching the spring, then it's got some velocity. Its MGH has changed, has gone up actually, but you've lost all the energy from the spring. And then from here, the only force on it then is gravity. So you've got a projectile which goes up and then stops at some final height, maybe right here. Awesome, and then laptop one. So let's go through the math of it. My pen. Okay, first I consider the time from A to B, when the spring is decompressing and the ball is moving up and it's speeding up. So what you do at point A is you've got, maybe we can do some energy bar charts. So positive is just positive energy and negative is negative energy charts. And so a lot of these are going to be positive by definition. You've got the spring is really loaded. That's the 1/2 k xa squared. And then depending on if we're going to define the 0 point of y to be at point B, then this actually starts off with negative. So maybe I should put a minus sign. mg, we call it xa, let's call it. So negative m times g times xa. So this distance right here is XA. Okay. And then plus it's not moving, plus 0. And there's no external work, as we decided before, because everything is internal to the system. Earth's gravity is internal to the system, and also the spring is part of the system. And then at point B, the spring has now gone to 0 energy, 0. The gravitational has actually gone to 0, because we defined 0 height to be at that point. And the kinetic energy is now all that momentum bar chart. So this one minus that one is going to give you that kinetic energy. And that's going to be 1/2 times m times v at b squared. So that's how you'd set up that equation using conservation of energy. So you can actually find, just as it loses contact with the spring, what's the speed of the ball? It's going to be 1/2 k x squared minus the mg x, I guess. And then you can go from B to C, same sort of thing. From B, we already did this. It's 0 plus 0, because we defined it to be 0, plus there's this 1/2, so plus and plus, mvb squared, plus 0, is going to be, when it gets to the top of its height, it's going to have, this one's still 0, plus now it gets all of its energy into gravitational potential and it stops. You get to the top of your path, that's when your velocity goes to 0. So it's just mg times whatever you want to define that to be, h max. So this distance from here to here is h max. Plus 0. So it's another way of solving without using kinematics. Okay. Times it. And so just a couple more slides, and then I'll finish up today. Which is, if you want, you can even skip the B step and go directly from A to C. This is one of the strong points of this entire method, is that if you go from one point to another, it doesn't matter where you went in between. The path doesn't matter. The conservation laws still apply, as long as you don't have any dissipative forces, which you don't. You just have spring, which is a conservative force, and gravity, a conservative force, meaning that you can just go straight from A to C and conserve the energy that way. Another way of looking at it, again, laptop's gone now, but if it were to fall, it doesn't matter what path it takes to get from the top of the book on the shelf to the book on the floor. The change in gravitational potential energy is going to be the same either way. So it doesn't matter what the path is, or if it goes up and then down or something like that. And this was similar, I don't know if you remember, when we had the two rocks thrown off the bridge. One was thrown up and one was thrown straight down. Those both had the same initial speed, so the same initial kinetic energy. They took different paths to get to the water, but they should both have the same final kinetic energy because of conservation of energy. So there's a nice, easy way to do a lot of these problems by just thinking about these things in terms of energy. So gravitational potential energy stores the work done against gravity, mg delta y. It increases with height, and it reflects the constant gravitational force near Earth's surface. And so I think that's all I'm going to do today. Don't forget, we're actually doing a Chapter 6 question in practicals this week. We've got a cart and a clamp, and you have an external impulse from the clamp on the cart that you're going to be measuring. So these are the sections to read ahead in Chapter 7 for Wednesday. Have a great time, and I hope to see you around practicals, or I'll see you on Wednesday.